Hi class, this is a follow-up video on using Kepler's laws of planetary motion and in particular how to apply them to figure out the best way to get from Earth to Mars. And this is something that we do from time to time when we send robotic spacecraft there, and people are thinking about potentially one day sending people there as well. So this is how you do it. You look at the sun and the four terrestrial planets right here. So we got Mercury, Venus, Earth, and Mars. And if we want to send a spacecraft from Earth to Mars, you might initially think you would wait until they are at their closest separation from each other, kind of like in this drawing, and then launch the rocket and just have the rocket travel straight to Mars and take the shortest path possible. And the real problem with that strategy is that if you launch the rocket from Earth to Mars, you're going to be constantly fighting the gravitational pull from the sun, and so that would require a lot of rocket fuel. So we can use Kepler's laws of planetary motion. This is the first one, which simply just states that planets take elliptical orbits as they travel around the sun, and the sun is at one focus of that ellipse. And these are, down here are some examples of ellipses. These are all ellipses. You have the circle, which is a type of ellipse, and then you can have ellipses that are more squished like this. And so that happens when you take the two foci and you separate them more. And the important thing to remember about Kepler's laws of planetary motion is that we call them the laws of planetary motion, but these laws hold for anything that is in orbit around the sun. And so that includes things like comets and asteroids. It also includes any satellite that humans would put into orbit around the sun as well. And so considering that, we can actually come up with a clever solution of how to get from Earth to Mars using the least amount of energy. And what we do is we use this thing called a Hohmann transfer orbit, and this was discovered almost 100 years ago. This strategy of going from one planet to another, and you will think about it in terms of going from Earth to Mars, but you can use this strategy to go from any planet to any other planet in our solar system. And it just comes back to Kepler's first law, which is that you can launch a satellite and put it into orbit, and you can put it into an elliptical orbit with the sun at one focus. The other focus would be here, and you can create or discover an elliptical orbit that touches the Earth's orbit at one point, and it touches Mars's orbit at the other point. And that's what I've drawn right here. And the sun is at one of the two foci. And so if you launch the satellite, and you'd have to launch it and you'd have to accelerate it a bit so that it wouldn't follow Earth's orbit, but it would now take this new Hohmann transfer orbit. So after you launch it, you would have to use some rocket fuel to accelerate the spacecraft a bit and get it into this trajectory. But once you do that, you can just turn the rockets off, and the spacecraft or satellite is just going to coast, and it's just going to obey Kepler's laws of planetary motion. So you don't have to use any rocket fuel from this point to this point. And you just wait until the thing takes this orbit, and then eventually it reaches Mars's orbit. Once it reaches Mars's orbit, you're going to have to turn the rockets back on so that it doesn't just continue taking this Hohmann transfer orbit. If you didn't do anything when the satellite got here, it would just come back to Earth's orbit in kind of along the same path that it left. But if you give it another acceleration up here, then you can get it to match Mars's orbit, and now it's going to be taking the same path and the same speed that Mars is. So when you do this, you have to time it, and so this is why you would have launch windows. You would have to have the Earth and Mars in a particular relative location so that you launch it here. It takes a particular amount of time. This is what you're solving for in your homework problem. And so you'd have to launch it when Mars is in a location such that during the duration of time it takes for the spacecraft to travel to the point where they're going to intersect, Mars would travel that over that same period of time right there. So you just have to time it so that you launch the satellite here, Mars is here, and then they both travel to this same point and they reach that same point at the same time. And then the satellite could land on Mars or do whatever. So when you solve this, you want to use Kepler's third law to calculate how long it's going to take for this spacecraft to travel from Earth's orbit to Mars's orbit. And just look at this picture right here. If you take the radius or semi-major axis of Earth's orbit, which you should know is 1 astronomical unit, and you add that to the radius or semi-major axis of Mars's orbit, you get this complete distance, which is the major axis. So this distance right here, which is the long dimension of this transfer orbit's ellipse, that would be the major axis of that transfer orbit. Then you cut that in half and you get something like this right here. That's the semi-major axis. That's what we call A in Kepler's third law. So given that you know that this is 1 AU, and you know that this is approximately 1.5 AU, I'll let you finish it off. You add those together to get the major axis, divided in half to get the semi-major axis. Use Kepler's third law to calculate what the period of this transfer orbit is. And then there's one detail at the very end, which is that if you're sending a spacecraft from Earth to Mars, you don't want the spacecraft to complete an entire orbit. You're going to want it to complete half of an orbit. So you only want it to go half of the way and then land on Mars. So when you calculate how long it takes to send a spacecraft from Earth to Mars, figure out what the semi-major axis is, calculate the period of that transfer orbit, and then divide that in half, since you're only going half of the way around the orbit. All right, and I hope that helps with solving this problem.